Okay, I think it's already time to start. So today we have François Greer. I don't know if I pronounced well, but he is going to talk about cycle-valued quasi-modular forms. So, François, please.
Thanks very much for the invitation. So maybe the real title of this talk should have been "Know the Lefschetz theory." It looks like you're going to do a study of that next week. So just to kind of sketch the main goal of Know the Lefschetz theory, let me just remind you. So suppose you have a family of surfaces. The first interesting example is K3 surfaces. So is a let's say one parameter family of K3 surfaces. And the question is, for which points in the base, so which B and B is the fiber of the family, the XB, having extra algebraic cycles. So in this case, it's just a curve class because we're on a surface, but more generally, you can have algebraic cycles in different dimensions. So I have extra algebraic curve class. Okay, so if we do an explicit example, for instance, a pencil of quartic K3s, to just take a one parameter linear interpolation family of quartic polynomials in 4 variables, you could ask how many of these K3s contain a line, or how many of these K3s contain a conic or something. And the answer to that question will be a finite number in the pencil. And the formalism I'm about to sketch tells you how to find those numbers. Okay, so just to set that up, let me just introduce some notation. So it's all about the polarized Hodge structure on the middle cohomology. So a weight 2 polarized Hodge structure is going to be a lattice lambda, first of all. So you should think of this as the polarized middle cohomology of signature 2, n. So I guess I'm doing K3 type here. For 2, n. If you wanted to do a more general surface, you would want to do 2p, n. There's some good reason why I'm going to restrict to the K3 type of Hodge structure later. So let me just assume it's 2, n right now. With the decomposition of the complexification into a direct sum of 3 complex subspaces. Such that there are 3 axioms that need to be satisfied. So the first axiom is this conjugacy axiom. So H20 bar is H02, and H11 bar is equal to H11. And the second axiom is orthogonality. So these HPQ is orthogonal to HP prime Q prime for P not equal to Q prime. So orthogonal with respect to the lattice pairing, which is extended linearly to this complexification. And then the third property is a definiteness property. What it says is that for all elements of HPQ, if I take the pairing of this element with its conjugate, then this is either positive or negative depending on the numerics. So Deligne's convention is the following. So omega bar times I to the p minus q is less than 0. Okay, so you should just think of this as some positive definite or negative definite condition. All right, so once we have this definition, it's natural to look at the set of all possible polarized weight 2 Hodge structures of this type on a given lattice. So I'm going to define D which depends on my initial underlying lattice, to be the set of all these possible Hodge decompositions. And because we're in K3 type, the whole Hodge decomposition is just determined by the line H20. So C omega, where omega is isotropic, and omega with omega bar is positive. Okay, so the key point here is that this omega spans H20, and this actually determines the entire weight 2 polarized Hodge structure, because we use these properties. So once you have H20, you have H02, which is just the conjugate. And H11 will just be the orthogonal complement of H02 plus H20. Okay, so if I look at this domain D, I can think of it as a subset of the projective space, projectivization of the complexification of lambda. Okay, so this is just some space of lines in this complex vector space. So now to do Noether-Lefschetz theory, I'm going to look at some codimension 1 subdomains of D that are determined by integral lattice vectors. So for each vector in my lattice lambda, we can define D of V perp, which is just the set of C omegas such that your omega is perpendicular to this lattice vector V. And this is a hypersurface. It's a linear section of this domain D. If we want it to be non-empty, we're going to need this vector to have negative self-intersection. That's just sort of a technical point. And the point is that if the omega from your polarized Hodge structure is orthogonal to V, then by Lefschetz 1-1 theorem or the Hodge conjecture in codimension 1, you get that this Hodge structure corresponds to a surface which contains an extra algebraic cycloclass. So to set that up, let me just go back to our family of K3 surfaces. So if we have our X to B, our family of K3 surfaces, we can record the Hodge structures of each of these K3 surfaces by a period map. So I'll call this map J. So this map just classifies the Hodge structures on the fibers. And I need to quotient my domain D by the automorphism group of the lattice. So O of lambda. This is an arithmetic group. And the reason why I need to quotient by that is that you need to identify the cohomology of each of these fibers with this abstract lattice lambda. And there's an ambiguity in doing that, which lies in O lambda. So for technical reasons, we actually take the stable orthogonal group O tilde lambda, but I won't say anything about that. Okay, so this is the period map, and then just to say what I was saying before, if I take the preimage under J of one of these hyperplane sections, so D of V perp mod gamma, then as a set, this is just literally the set of all points in the base of the family, such that H11 of XB contains an integral vector. Okay, so H2, if we take the H2 of XB primitive and choose an isomorphism with this lambda.
François, I think your iPad got disconnected.
Okay, thanks.
Just a minute.
Mine? No, I'm here.
No, I am talking with François.
Oh, sorry. I thought you talked with me.
Okay, is it?
But I don't have the whiteboard anymore.
Okay. Okay, let me try to log back into the meeting with the iPad. You can still hear me, right?
Yeah, but your iPad is
Yeah, my iPad's off. Okay.
not logged in.
Sorry about that.
Recording in progress.
Okay, you see again now.
Okay, so we're back.
Continue.
Okay, so this is the definition of these Noga-Lefschetz divisors inside of the quotient d mod gamma. And it's a good idea to assemble these together, keep track of all these together for different vectors v. So to do that, I'm going to define a divisor C sub n gamma to be the union over all vectors in my lattice dual, such that the square of the vector is minus 2n, and the class of the vector is equal to gamma in the discriminant of the lattice. So we're taking d v perp mod gamma inside of d mod gamma. Okay, so there's infinitely many vectors, integral vectors, and they all have different self-intersections and different classes in the discriminant lattice. So I'm just trying to organize them into some finite divisors. And so if we organize them in this way, it's called a special cycle. And these divisor classes actually form the coefficients of a modular form. So that's the first theorem that I want to state, and it's by Borchards. So what Borchards defines is he defines this formal generating series in this variable q. So phi of q might look kind of familiar if you do Gromov-Witten theory. So it's a sum over all n greater than or equal to 0 and over all gamma in lambda dual mod lambda of the class of this divisor times q to the n times e to e sub gamma. So what is this? So this is a formal power series. It lives in cohomology of d mod gamma, h upper 2 d mod gamma. This is, if you think of this as Borel-Moore homology, because these special cycles are non-compact, and the period space is also non-compact, but it is codimension, real codimension 2, complex codimension 1. So tensor the group ring of lambda dual mod lambda, and then also tensored with formal power series in Q. Okay, and I have to say one more thing, which is that this definition doesn't quite make sense for n equals 0. So there's a sort of a special definition in that case. So C0 is defined to be, or C00, rather, is just defined to be the first Chern class of the Hodge bundle dualized. The Hodge line bundle is just a bundle on d mod gamma, which whose fiber is just this C omega that's classified by D. Okay, and so far this is not a theorem, this is just a formula, but the theorem says that this power series is a vector valued modular form.
What is the gamma? I don't.
Yeah, it's just a formal variable. So the discriminant of the lattice is just a finite group, a finite abelian group, and so E gamma is just a basis vector labeled by gamma.
Okay.
Yeah, if this is your first time seeing this, you might want to just assume that the lattice is unimodular. So then you can just forget about all these lowercase gammas and just keep track of n. So maybe it's easier to read. So the weight of the modular form is half of the rank of the lattice that we started with. So if you remember, we chose a lattice of signature 2 comma n, so that's n plus 2 over 2. And by vector valued modular form, what I mean is that there's a certain representation of the metaplectic group, which is this double cover of SL2Z, on the group ring of lambda dual mod lambda. So acting on these E gammas. And this is called the Vey representation. I'm not going to say what it is. It's a standard thing. And once again, if this is the first time that you're seeing this, I think it's easiest to just assume that the lattice you're dealing with is unimodular. And so then this vector valuedness is sort of trivial. It's just a classical modular form for SL2Z. So that's the statement by Borchards. And how can we use this state to study these numerical problems? Well, if we take our phi of q and take the intersection product of every coefficient in this power series with the class J of B, so the image of our period map, this gives an honest modular form. Right, so just pairing H2 of D mod gamma with H lower 2 D mod gamma. And this goes to Z. Okay, so for instance, the first term of the series will be the degree of the Hodge bundle for our family of K3s. The second term will be the number of K3s that contain a line. The next term after that will be the number of K3s that contain a conic, and so on and so forth. The point being that these special curve classes are classified by some integral vectors in the cohomology lattice. And we're just requiring that they be algebraic classes in these K3s. Okay. So that's the nice story. People have used this to compute some Gromov-Witten invariants of certain Calabi-Yau threefolds that are fibered by K3 surfaces.
So modular form for SL2Z, no? Even or
SL2. Well, so yeah, for MP2Z, the way I've written it, but yeah, that's basically just a mild generalization. You can take it to be SL2Z with higher level if you like. That's equivalent. So yeah, so just this is a modular form in the classical sense. Okay, so the question that I want to talk about today is pretty natural from the perspective of geometry, which is, what if this family is not smooth? So what if this family X to B has singular fibers? And if you have some experience with algebraic geometry, you might have noticed that it's actually quite rare to produce families over a proper base where all the fibers are smooth. This almost never happens. So in that case, you only have a rational period map from the base of your family to D mod gamma. And okay, if the singular fibers are mild, like they're, say, ordinary double points, then Hodge structures of these singular K3 surfaces are still pure Hodge structures. So that essentially means that you can extend the period map everywhere over all of B. And that will be the case if you can take a general pencil of chordic surfaces, for example. So that's not a very serious problem, but there are examples where the singular fibers are worse than just having ordinary double points. So for example, if you degenerate to a simple normal crossing surface or something. And in that case, the period map is not extendable. So it's really a rational map to this D mod gamma. And so you can ask, how can this theorem be salvaged in that case? So I'm interested in the case where this period map is strictly a rational map. I'll give an example of that later on in the talk. So one natural thing we can do is we can compactify D mod gamma. There's sort of a universal way of doing that due to Bailey and Burrell, and then extend the period map to this compactification. Okay, so this is the the Bailey-Borel compactification. And this works quite generally for any kind of Shimura variety. So the example that I'm doing right now is the type 4 case. So this is the case of K3 type Hodge structures, but this compactification kind of exists very generally. And just to describe for you what happens when you compactify, it's very analogous to the situation of a modular curve. So you add some rational boundary components. Are added to D. Before you quotient by gamma, you add these rational boundary components to D. And they, in this case, they're labeled by isotropic sublattices. So the compactification D star is going to be D union over all J. So J is going to be an isotropic to inside lambda. And each of these J's gives you a upper half space, upper half plane, and then also union over all I's of some points, P sub I, where I is ranging over all isotropic one-dimensional, I guess, lines. Okay, and then D mod gamma star is just defined to be D star mod gamma. So this is literally actually in the case when n is equal to 1, this actually recovers the construction of modular curve compactifications just for H mod SL2Z. So if you're familiar with that, in that case, you just add all the rational points on the real axis as well as infinity, and then SL2Z acts on those rational boundary points, and the quotient gives you a compact Riemann surface, a compact modular curve. So this is just a mild generalization of that. So now we have, instead of just points that we've added some points, but also some upper half planes, which then get quotiented to modular curves in their own right. Okay. So this is the Bailey-Borel compactification, and the big problem with Bailey-Borel is that it's not smooth. So Bailey-Borel is very singular. So Mumford and his co-authors solved this problem by finding natural ways of resolving the singularities in this Bailey-Borel compactification. So the toroidal compactifications are blowups of the Bailey-Borel compactification, and I can describe for you in terms of the set what the boundary looks like. So we use capital sigma to denote our toroidal compactification. And as a set, it's just D mod gamma, the interior, union with a collection of divisors that are indexed by J. So here, J is as before, is a two-dimensional isotropic, but we're only looking at the set of J's up to the action of our arithmetic group gamma. So that's a finite set. And then union over all orbits of the I's of some divisors indexed by I. I'm calling them TI because they're actually toric varieties. That will come out of the construction. And there isn't a choice here. So the sigma that's in the notation refers to a choice of gamma admissible fan in the positive cone of a certain hyperbolic space. So to be precise, it's if you take I perp mod I, where for each of these isotropic lines, this is a hyperbolic lattice. So lattice signature 1, n minus 1. And we're taking the positive cone there. So just to draw a picture of that. So in the case where n is equal to 2, I can draw the cone. So it's some cone in 3 dimensions. and I'm choosing some kind of polyhedral decomposition of this cone. So you should think of it as some kind of Escher type picture, so some kind of infinite honeycomb decomposition of this cone. And there are various natural ways of selecting one of these structures, and for each such admissible fan, you get toroidal compactification, which will be smooth, and it will be, like I said before, a birational blow up of the Bailey-Burrell compactification. So very useful terminology is people have referred to the interior of the period domain as type 1. And then the first sort of type of boundary is type 2, and then the deepest part of the boundary is type 3. So in this blow up, they're all divisors, but before we did the blow up in the Bailey-Burrell compactification, if I just go back to the previous slide. Yeah, so in the Bailey-Burrell picture, type 1 is the sort of generic part of the period domain. Type 2 is the part which is one-dimensional boundary, and type 3 is the cusps in the boundary. So just the one zero-dimensional part of the boundary. Okay, so now I'm ready to state the second theorem, which I'll label by Roman numeral 2. So if I take this Borchard series that I had before, I just take the closure of each of the coefficients. So phi2 of q is going to be defined as, again, sum over n and gamma as before, of the class now of Cn gamma closure q to the n e sub gamma. Again, if this is your first time seeing it, you can just ignore the e gamma and just assume that gamma is just 0. But so now this lives in h2 of d mod gamma 2 answered with formal power series. The theorem says this is a vector valued quasi-modular form. Okay, so I should say, what do I mean by this? So d mod gamma 2 just means I take the partial compactification where I've just taken the first two pieces of this stratification. So I'm taking the interior and then I'm adding in all the boundary divisors of type 2. So these divisors that are indexed by J, and I'm leaving out the worst type, so this type 3. All right, and so if I do that, I end up with a quasi-modular form. Now, what's a quasi-modular form? For our purposes, it's just going to be a polynomial in the E2 Eisenstein series with coefficients in classical modular forms. Okay, so I'll just write a polynomial in E2 over classical modular forms. All right, and then the second part of the theorem is that we can say precisely how the presence of E2 measures the boundary. So we can take the derivative with respect to E2 of this power series, E of Q. And we end up with a new power series, which is actually modular. So we end up with, to be precise about it, it's the sum again over all j's up to the action of gamma of the theta function of j perp mod j, which is a negative definite lattice, times the divisor dj. All right, so you can think of this as what's called a holomorphic anomaly equation.
So it is degree 1 polynomial in E2 with this.
Exactly. Yeah, it's just a degree 1 polynomial in E2. Yeah. That's essentially because we're in signature 2, n, because we're in K3 type. But yeah, it's just it's a very, very simple differential equation here.
By the way, this algebraic closure of nodal left both sides C and gamma. This C bar is not compact necessarily because you didn't make the full compactification.
That's correct. That's correct. Yeah. So we're still taking these classes in H2 of a non-compact, H upper 2 of a non-compact space, which you're allowed to do. You know, if you have a non-compact cycle, that still gives you a class in H upper 2. But so the third theorem, so I'm indexing these theorems by Roman numerals kind of in a suggestive way. So the last theorem is going to be, so by the way, I should say this theorem 2 is due to me, and this theorem 3 is due to myself and 2 collaborators, Phil Engel and Salim Tayou. And you can kind of guess the statement almost at this point. So I want to take the closure now in the full compactification. So now it's actually a compact cycle. And again, it's going to be the sum over n gamma of the closure of C n gamma due to the n gamma, which is now inside H2 d mod gamma sigma. So just the full toroidal compactification tensor, same stuff as before. And the statement is that this is a vector valued Mach modular form. So that's a further generalization of quasi-modular form, and it includes some really more exotic kinds of series. And we also have a holomorphic anomaly type equation, but it looks a little different. So instead of just the partial derivative with respect to E2, we use these Zagier shadow operators. There's a Zagier operator that he denotes with a xi, which goes from Mach modular forms weight k to 2 minus k. And so if you apply this operator to our power series, we have a formula for what this is in terms of the rays of the fan. So maybe I won't write the formula right now because I don't know if it's so useful, but just let me say that there's sort of an analogous formula for what happens when you apply this kind of lowering operator of Zagier to the power series. Okay, so maybe it's a good time to stop for any questions at this point before I go into the proof.
Sorry, I have a question. So this gamma, which is your, so to say, monodromy group, right?
Yeah.
So it does it have some extra properties like being arithmetic or things like this? So I mean, this d over gamma is a Ball quotient or something like that?
Yeah, that's a great question. I was just assuming that gamma was the full arithmetic group, so the full automorphism group of my lattice that I started with.
Oh.
You're right that in order to define the period map, it's sufficient to just quotient by the smaller group, which is just the monodromy of your particular family. But I'm doing that. I'm quotienting by a larger thing. And you actually do need to quotient by an arithmetic group if you want this Borchardt's theorem to be true. It's an interesting question, actually. If you quotient by a smaller group, by one of these, I mean, there are monodromy groups that are quite thin, and I don't know.
Yes.
Yeah, I don't know if there's a modular form type statement for those smaller groups, actually. So that's a good question.
I see.
Yeah, I'm quotienting.
Thank you very much.
Yeah.
Okay.
Maybe one question. So these results depends on the compactification, or they are independent?
Absolutely. Yeah, it depends on the compactification in a very essential way. Yeah. So we'll see that, I guess, in a second. But I should say that the type 2 partial compactification is independent of the choice of fan. So if you like, theorem 2 is completely canonical. There's no choice there. But in theorem 3, when you have the cuspidal boundary, that actually does depend. Okay. So let me just say a few words about the proof. Okay, so to prove that it's a cycle valued modular form, it suffices to just intersect with test cycles. So let mu inside H lower 2 of my compactified period space just be an arbitrary class. in homology. I'm going to take it in rational homology because these intersection products are actually, I mean, they're defined over Q. So to take a test cycle, you need to prove the following lemma, which is that mu can be composed into mu1 plus mu2 plus mu3, where mu1 is a compact cycle that's supported on the interior. So it's in H lower 2 of D mod gamma. mu2 is in direct sum of H lower 2 of the DJs. So it's supported entirely within the type 2 boundary. And mu3 is supported entirely inside the type 3 boundary. So it's inside the direct sum of H2 of these divisors that I called T sub I. So these are the toric divisors that lie over the deepest stratum in the Bailey-Borel boundary. Okay, so once you've split, so this requires a proof, and I won't say what it is, but it uses some spectral sequences, kind of standard topological methods. But once you have that, then if you want to intersect your test cycle with the power series, P sigma of Q, you can just do 3 separate computations. So first you intersect it with with mu1, mu2, mu3. And the point is that because mu1 is interior, you can just do this first intersection with the original Borchard's form. And these latter 2 intersections actually require that you work with the boundary. So this first one is going to be a modular form by our first theorem one. So modular form by the Borchard's theorem. So for these 2, I need to actually compute explicitly what you get. So compute explicitly. But the point is that computation, whatever it is, occurs completely inside the boundary because I'm intersecting a test cycle supported on the boundary with a bunch of divisors which are meeting the boundary transversely. So I just need to describe what the limits of these Noether-Lefschetz cycles are in the boundary of our compactification. So let me just go ahead and do that now. So I need to tell you a little bit about what the boundary looks like. So in type 2, remember the components of the boundary in type 2 are indexed by these J's, which are rank 2 isotropics. So if you look at the numerics, J perp mod J will be a negative definite lattice. So signature 0, n minus 2. And so the for J is actually fibered over a modular curve, so H mod SL2Z. This modular curve is the Bailey-Borel boundary component, and this DJ is the exceptional divisor of our blow-up. And so this fibration is just the universal family of elliptic curves over that modular curve, but then self-fibered product with itself, n minus 2 times. So I can write that as tensored over Z with J perp mod J. So here I'm thinking J perp mod J just as a free abelian group of rank n minus 2. And if I tensor an elliptic curve with that free abelian group, it's the same as just taking a self product of that elliptic curve. So it's really an abelian, a fibration by abelian varieties. But each of the abelian varieties is just a power of an elliptic curve. Okay, and then there's a slight one more detail, which is that you need to quotient by the Weil group of this J perp mod J, which is a finite group. Quotienting by finite group doesn't really affect intersection products too much, so I'm not going to worry about that. But just to be completely correct, that is happening. So okay, so that's what DJ looks like. Now, if V is our lattice vector that's defining the Noether-Lefschetz cycle. If V is perpendicular to J, then D of V perp will meet this boundary divisor, meets what we're calling DJ. And it will meet it in just a hypertorus. So it will meet it in, if I look at the class of V in J perp mod J, perp inside of this torus DJ. And on the other hand, if your V is not orthogonal, so if V is not orthogonal to J, then dV perp will miss that boundary component completely. So the contribution to the power series ends up just being a sum over all classes in J perp mod J of the intersection number of this hypertorus with the test curve times the self-intersection of that vector. And so if you sort of write out what you get, you end up just getting a theta function for J perp mod J, but then you take the Q derivative of the power series, and taking a Q derivative of a modular form produces a quasi-modular form. That's kind of maybe the original intent of introducing quasi-modular forms, is that they're a differential graded algebra. So they're closed under this derivation operator of differentiating the series with respect to Q. Okay, so that's kind of the sketch for type 2. The type 3 boundary is a little bit more complicated. So how to describe the type 3 boundary? So the picture is, for each of these isotropic lines I have I perp mod I, which is now a hyperbolic lattice, so the signature 1, n minus 1. And if we look at the real points of it, it contains this positive cone, and we've chosen a locally polyhedral decomposition of the cone, which is equivariant with respect to the action of gamma, or rather the stabilizer of I inside gamma. Okay, so gamma I acts on this cone, and we're assuming that it also acts on this polyhedral decomposition. Each ray in the cone gives a divisor, gives a toric boundary divisor. And the way that you find the toric variety is just by kind of projectivizing. So if you have a ray in this cone, if you quotient the vector space by that particular ray, and just look at the induced fan on the quotient, so it's just kind of taking the cross section as I drew it, then the complete fan gives you a toric variety, and that is exactly what the boundary divisor is. Okay, so just to sketch the computation, you end up if you try to calculate what the how these nodal Lefschetz divisors intersect any given test cycle. A test cycle in this case can be assumed to be a toric curve, so that corresponds to a codimension 2 facet of this polyhedral decomposition. So you get a theta series with a piecewise linear weighting. So this is just a completely toric computation. The nodal Lefschetz divisor gives you some kind of hyperplane section of this cone, and then you just use kind of formulas from toric varieties to write the intersection numbers in terms of a piecewise linear function. So you can think of this as some kind of tropical version of the previous Borchard's result. Okay, so that's kind of the summary of how you prove this. You essentially just do it one by one, reduce the computation to an explicit study of the boundary. So the last thing I want to do is give maybe a geometric application of this kind of result. So why would you care, right? So modular forms are useful. So sort of, I would say, two advantages of this kind of theorem. So one is that spaces of modular forms are very small. So we have finite dimensional spaces of modular forms. So if you have a theorem like X series that comes from geometry is a modular form, if you know the first few coefficients of the series, then you know the entire series. That follows from finite dimensionality. So this gives you kind of a lot of leverage, allows you to compute infinitely many things just from knowing finitely many of them. And the second advantage I would say is growth rates. So using contour integrals, there are precise estimates for the growth rates of the coefficients of a modular form. And we have similar results for these more general things like quasi-modular forms and mock-modular forms. So for example, Davish Malik used that to prove the Tate conjecture for K3s, so that some kind of cusp form growth rate estimate was an essential ingredient in that proof. And I'm going to use something similar in the following application. So this is still in progress, but I think it's exciting. So the application is to the severity problem for a rational elliptic surface. Okay, so in general, if you're given an algebraic surface with a line bundle, so let's say an ample line bundle, so polarized algebraic surface, you can look at the complete linear series of that line bundle, and there are subvarieties of that linear series whose points correspond to curves that have singularities. So V sub h, where h is between 0 and G, where G is the genus of curves in the linear system, is going to be defined as just the set of curves in our complete linear series, such that the geometric genus of the curve is equal to h. So if you'd like, we're looking at curves that have G minus h nodes generically. Okay, and so the severity problem is to decide whether these severity varieties are irreducible or not. So that's the severity problem. Is VH of L irreducible? So the only complete solution is for P2, and it's due to Joe Harris from the 80s. So for P2, the answer is always yes. I believe it's 86. For Del Pezzo surfaces, the answer is yes, but only for h equals 0. We don't know about for higher genus, but if you're just looking at rational spaces of rational curves on a Del Pezzo surfaces, then it is true, with one exception. So except kind of there's a trivial exception where the severity variety is 0-dimensional, so it's just some finite set of points. Except when the severity variety is 0-dimensional. Okay, so and this is due to Testa from O2. And so the theorem that I want to state today, it's, like I said, it's still in progress, is that for the rational elliptic surface, so for the blowup of P2 at 9 points that are the base points of a pencil of cubics, h equals 0 is already false. So essentially showing that the Testa result is sharp for these surfaces. Okay, but so maybe the methods are kind of more interesting maybe than the result. So as is often the case, so I'll just kind of sketch the method. So I'm going to take I'm going to take a rational elliptic surface. So this is kind of the simplest example of a non-trivial elliptic fibration. So this is fibered over P1. I'll call it R for rational elliptic surface. I'm going to take L to be a bisection line bundle. So it's a line bundle that has degree 2 over the base. Okay, so elements of this linear system are going to correspond to some kind of hyperelliptic curves, genus G, that are fibered over P1. And so the severity variety in this case is actually a curve if you do the numerics. So so v sub 0 of L is equal to a curve. And these correspond to, points in this severity curve correspond to elements of the linear system that are rational curves. So they have a bunch of nodal singularities. Okay. So there's a universal family, so we can look at all these rational curves, C over V0 of L. But more generally, I can just look at double cover, any double cover of the base of the base P1, and form the base change of my elliptic fibration by that double cover. And the base change will always be a K3 surface, elliptically fibered K3, so it'll be a very special K3. So it lives actually quite deep inside the nodal Lefschetz stratification. But this construction then gives me a family of K3s indexed by double covers of P1. So this is actually a 2-parameter family of K3 surfaces. And I therefore get a map from the base of my family to one of these D mod gamma spaces. Okay, and it turns out that these severity curves, if you keep track of the branch points, the 2 branch points of any of these double cover curves, this embeds all of my severity curves into the Sim2P1 space, and these agree exactly with the nodal Lefschetz divisors. So, so you can realize these severity curves V0 of L as nodal Lefschetz loci in the space of double covers. Okay, so then that means that our mock modular form, our quasi-modular form theorems can tell us the degrees of all these different severity curves. So the severity curves are indexed by their genus, by L squared, which is 2G. So there's a formal power series, which ends up being a weight 10 modular form, which counts the degrees of all these severity curves as curves inside Sim2P1. And the number of singularities that these curves have are then counted by another modular form, which is the sort of codimension 2, so the places where 2 nodal Lefschetz divisors intersect. And that is a Siegel modular form, and so it also has a growth rate estimate. And if you can show that the number of singularities exceeds the genus of a plane curve, then you've essentially shown that that curve is reducible. So that's kind of how the proof goes. So if the number of singularities in V0 of L exceeds the genus degree formula, that implies that V0 of L is reducible. Okay, so maybe I'll stop there. Thanks for your attention.
Okay, thank you, François. Maybe G, stop.